So I'd like to spend a little bit more time on airfoils today. Now, I'm not going to go back through the thin airfoil theory. I think I covered that pretty extensively last class period, and I posted that recording online. So you should be able to go through. We went through thin airfoil theory in quite a bit of detail last time around. So I'm not going to do that today. Instead, I'd like to take a step back and make sure some things are clear just on a real fundamental level here, okay? So let's say that we have an airfoil and we would like to measure the forces that this airfoil produces, right? And today we're gonna pretend like we've got a wind tunnel. That's how we're measuring it. So I'm gonna take this airfoil and it looks like this. And I'm going to put it in a wind tunnel. And in order to measure the forces on this airfoil, I've got to choose how I'm going to connect this airfoil and measure forces off of it, right? So most of you have probably had instrumentation. You're going to have to figure out some way to hook up this airfoil and measure these forces and moments. Well, today what we're going to do is we're going to put it on a little thing like this. So we're going to attach it right there, and we're just going to happen to choose the center of that airfoil. Okay, so this is the x-axis and the y-axis, and we're just going to put it right at the center. Remember, this is our chord, and we're going to put that right at the midpoint there, and we're going to put some strain gauges in there and different methods for measuring things. And so what that's going to give us is and then we're going to run the wind tunnel. So let's turn on the wind tunnel. We've got some velocity here, and we're going to measure a force coming off of this. Okay, and we're going to measure two things. There's a force that we're going to pick up on here, and there's also going to be I'll put this in a different color so you can see it, but there's also going to be a moment about that pivot, right? And so we're going to have to measure what that moment is and be able to withstand that. Obviously, just like we're withstanding the force by using, by pinning it, we're gonna have to be able to hold that moment, but also measure what it is, okay? So out of this wind tunnel test, we get a force and a moment, okay? So now I want to see how that's gonna change as I change the angle of attack. So now I'm going to rotate that airfoil. We're gonna do this, and I'm still pinning it at that same point. And so now my coordinate system for that airfoil looks something like this. We have X in this direction, Y in this direction. And we've got our free stream velocity still coming in here from, because it's horizontal in this wind tunnel, right? And again, we're going to get another force out of this, and we're going to get a moment. Okay. And I could actually repeat this process at a number of angles of attack. So we're just going to look over here for a second and say, as I change angle of attack, what are the measurements that I'm taking on this? Now, the force is changing in magnitude and direction. So yes, this meeting is being recorded right now. So you'll be able to go back and watch this. Yeah. Okay, so the force gives us a magnitude and direction. Those are actually vectors up there, right? So that's a force vector in 2D because we're working on a two-dimensional thing here. So what's a good way to report that force? You guys have any ideas? Well, how would we express the direction of that force, for example? It's going to change in magnitude and direction as we increase it. Okay, in X and Y, we can report the X and Y components. What do we call that if we were to divide that up? So I'm just going to draw that here in green. So that force could be divided into X and Y components. What's the X component called? Okay, we got one of them. The Y component is called the normal force. The X component is what we call the axial force. Now, it just so happens that at 0 degrees angle of attack, the axial force is right in line with V infinity. See, if we came over here to this other drawing, the axial force is in this direction, and the normal force is in this direction because those are perpendicular or parallel to our X and Y axes, right? So we can get the normal force and the axial force, and we could have those, you know, for each angle of attack. We could fill this out and compute the normal and axial forces. Okay. Okay, what's another way to report these forces? Okay, lift and drag. Lift and drag is the same expression of force. It's just that we're looking at the components relative to V infinity instead. So, so for example, over here we'd have lift is always perpendicular to V infinity. So that's our lift, and drag is always in the same direction as our velocity. Okay, so we could compute or report those in terms of lift and drag. All right. Now, what if we already computed them in normal and axial, and now, or let's say that we computed them in lift and drag. Okay, so we had all the lift and drag data, and now we wanted to get the normal and axial. Do we have to go back and rerun the experiment to get normal and axial, or how do we compute normal and axial relative to lift and drag? Well, it's just a rotation here, right? We know the magnitude and the direction. We can compute it for the others. So for example, the normal force, if I had the lift and drag, it's equal to L times cosine alpha plus drag sine alpha. And the axial force is drag cosine alpha minus lift sine alpha, right? So if I had lift and drag, I could compute normal and axial, and actually you can go the opposite direction as well, right? So we can get an expression here for lift and drag as a function of normal and axial just as easily, right? So we can go either way, right? Okay, great. So let's look at what these would look like. So we know that as a function of angle of attack, if I were to plot lift, and I'm so used to putting that in coefficient form, but let's just say it's lift like this, then we would expect from thin airfoil theory, we would expect that data to be pretty linear, and that's exactly what we're going to find. We're going to find that lift data is really close to linear. Now we're going to get up to some angle of attack where the airfoil stalls, and what that means is that the flow is going to separate off the top here, and we're going to lose lift, right? As long as the flow stays attached, this is going to be fairly linear. So up to some point, it's going to look about like this, and then it might drop off past that once we stall. Now let's look at what and let's look at what drag would look like. So if we were to plot drag as a function of angle of attack, it turns out that drag is often very, very nearly parabolic with angle of attack. Okay, so now this is maybe a little bit confusing here because on potential flow, it says that the drag is 0 always, right? But here we're in a wind tunnel, we're going to measure some drag. So we've got some finite drag here, but potential flow would say that the drag is always 0. Okay, so what would the axial, the normal and the axial forces look like if we plotted them on here? So this is lift and drag, and let's overlay some normal and axial on here. Well, it turns out if we look at the normal equation here, we can kind of assume what this is going to look like. So it's the lift times the cosine alpha. Now remember, alpha is small. We're going between 0 and 10 degrees or something. So cosine of alpha is going to be really close to 1. And then plus the drag times the sine of alpha. Now the lift is usually on the order of maybe 10 times what the drag is. So drag is pretty small here. And then the sine of alpha times drag is small too. So sine of alpha, we can swap that out for alpha for like a small angle approximation if we wanted to. But that's a small number times a small number. So there's a really small component multiplied by lift or compared to lift times the cosine of alpha, which is close to 1. So it turns out that the normal force is almost identical to the lift. So we're just going to say that this is our normal force if we were to plot it on here. It's really, really close to what we'd get for lift. Now, drag and axial, let's compare what those look like for a second. So here's our axial force. It's drag times the cosine of alpha. So cosine of alpha, again, alpha is really small, so this is really close to 1. So it's going to be drag minus the lift, which is 10 times bigger than drag, times the sine of alpha. Now, sine of alpha is really small. It's alpha compared to 1 here, right? So we've got about a 1 here and an alpha here. So so it turns out that we've got something drag that's 1/10 the size of this, but it's being multiplied by something large, and then lift, which is large, multiplied by something that's small. So at small angles of attack, what happens is the axial force is really close to the drag force, but it turns out that as we move away here, the axial force gets dominated by the lift. Okay, at higher angles of attack, then the lift component here becomes really important. And notice that there's a negative in front of that. And so as alpha gets big, we get large negative values here. Okay, so you can look on page 469 for more beautiful plots like this. This is on page 469. It shows you what these plots would look like for a complete aircraft. They're basically identical, though, or same trends that we see for an airfoil. Okay. So some people often think that drag and axial force are very similar. You know, I guess in some respects they're kind of similar, but their magnitudes can be very different. So you want to be careful about that. That the axial force can actually be negative. Notice that we've got a negative number here. That's not uncommon for an airfoil or an aircraft to have a negative axial force. But that doesn't mean that drag always stays positive. Drag is always positive. The force that's in line with V infinity is always positive, or 0 in the case of potential flow for a two-dimensional airfoil. But in general, drag is positive, but the axial force can be negative. Some people in the industry call this leading edge suction. Okay, the fact that the axial force can be negative, they call that leading edge suction, and they approximate it as minus L times alpha, or minus L times sine alpha. Okay, that's what they call the leading edge suction. But all it is the force in the axial direction, and it turns out that it's negative once it becomes dominated by lift instead of drag. Okay, do they mirror each other exactly? I'd have to think through that a little bit more. I know that it comes back down over here. I'd have to think through that. No, they don't mirror each other, though. I think that was the important question there. So drag and axial do not mirror each other exactly. Okay, so let's look at this pitching moment. Remember, we not only studied the lift and the drag, but we also studied the pitching moment. And maybe before we leave lift and drag, axial and normal, let's talk about how these are non-dimensionalized. So we usually talk about things in terms of a coefficient, a force coefficient, like a lift or drag or axial or normal coefficient. And what that is that force divided by 1/2 rho v squared. This is the dynamic pressure, right? And then this is actually a section force. I should have had little tildes on all of these because these are just a section force, but it's the section force. And so we need a length here. We usually use the chord of the airfoil when we're talking about an airfoil. So this is how we non-dimensionalize. We use this exact same denominator to non-dimensionalize every one of these forces, okay? So all of these are non-dimensionalized the same way. Okay, and remember, this is a force per unit span. So all of these forces, lift, drag, normal, axial, those are per unit span. And so you would then multiply that by the span if you wanted to get an estimate for the three-dimensional force, you know, or the actual force in newtons. But this is a force per unit span. So this is newtons per meter, for example. Okay, let's look at the moment. So we also recorded the moment in our data set here. So we've got this moment, and I'm going to say that this was the moment at c/2. Okay, so we chose this location c/2 as this location where we pinned the airfoil, and so we have moment information at every point along there. What can we use the moment information to find? There are two key things that we can use that pitching moment information to find. Any thoughts? Okay, center of pressure. Center of pressure and aerodynamic center. Exactly. Let's start with center of pressure, okay? So let's use it first to find that. Now, actually, let's take a step back for just a minute before we look at the center of pressure. Let's talk about what this moment means in general. So we've computed this moment at this location, and we also computed a force, or normal and axial, lift to drag, whatever. However we've expressed that force, we have that information from this test, and we also have the pitching moment. Well, what if I wanted to know what the pitching moment was at another location along the airfoil? You know, the quarter chord is something that's of interest to us, or the leading edge. The leading edge is a nice place to think about, although that information is not super helpful. But what if we wanted to figure out what the moment was at another location here? Well, let's work through that and figure it out. Let's start with the leading edge. So the moment at the leading edge, how would I compute the moment at the leading edge? Well, it would be, if we just turn this into a statics problem, I've got a force and a moment here, and I've drawn that moment in the positive direction. It may have a negative value, but I've drawn it in the positive direction, just like I always draw the normal and the axial forces in the positive direction, but it may turn out that the numbers are negative, right? So I've drawn this as a positive pitching moment. Positive pitching moment is nose up. So I want to figure out what the pitching moment would be here at the leading edge if I knew the pitching moment at the half chord and the forces. Now, the only force that matters here is the normal force, because the axial force lies right along the chord line, and I'm trying to figure this out at the leading edge. So the axial force doesn't play into this. So the moment at the leading edge would just be equal to the moment at c/2, and then minus the normal force, n times x, which would be c/2. Let me, anyway, that's this distance here. I'm just going to call that x. Okay. So actually, it turns out that in general, we can write this. In fact, I'm just going to pretend like we didn't know, or that it doesn't have to be c/2. It can be the moment at any x location. If I knew the moment at any location and I wanted to get it at the leading edge, I would just take the moment that I know minus the normal force times the x value of where that moment is, and that would give me the pitching moment at the leading edge. Everybody okay with that? Okay, now let's look at this in non-dimensional form. So we know that in order to non-dimensionalize the normal force here, we're going to do n over 1/2 rho v squared c. Okay, and now I want to non-dimensionalize these other things. So mx, the way I non-dimensionalize that is 1/2 rho v squared, and I actually need a c times a c because it's a moment. So before we had a force, and now I'm going to have a c squared there. That's the same with this moment at the leading edge. Same way, so rho v squared c squared. And then we've got an x over here. And because see, I've divided everything through by this value here. 1/2 rho v squared c squared, divided that, divided this, and I have one extra c that I need to divide through by, and that's conveniently going to go right under that x there. So now x is non-dimensionalized. Normal force is non-dimensionalized, pitching moment. So the way we usually write this is Cm at the leading edge is equal to Cmx minus Cn times x over c. Okay, so that's the same equation in non-dimensional form. All right. Okay, so this is pretty powerful. We can move moments around to any location, which means that we can also compute the moment at locations of interest. So I can write an equal sign here and say this means that, so if I had the way we were looking at this equation is that we had some wind tunnel data where we knew where the pitching moment was taken, and we were trying to compute the moment at the leading edge. But this is true for any point on the airfoil if I knew the pitching moment there. So let's say that we wanted the pitching moment at the center of pressure. Now I don't know where that is right now, but I'm just going to write this equation. So the pitching moment at the center pressure minus Cn times xCp over C, right? This equation has to hold true because this is the pitching moment about some location, and that location in terms of x over c. So this all has to hold true here. Well, that means that we can skip this step of even computing the pitching moment at the leading edge. If I want to find the location of the center of pressure now, all I have to do is solve this equation. Remember, I have all this information from my wind tunnel test that was given. All I have to do is solve this equation for xCp over c to now find the location of the center of pressure. And we need to apply one condition. What's the one condition? What's the definition of center of pressure? The definition of the center of pressure. Okay, it's the location where the pitching moment is 0. So that means actually at the center of pressure, this guy is 0, right? Well, that's nice for me because now I can solve this equation for the center of pressure. And the way we do that is we just divide by minus Cn across the whole thing. So what I'm going to get is xCp over c is equal to, if I divide by negative Cn on the left-hand side here, I'm going to get an x over c minus cmx over cn. Did I do that right? So that's my center of pressure location. So if I know the pitching moment at any x location, and now we've got to remember that this x location here, and maybe I'll just circle it, this x location is tied to this x location. Those have got to be the same, right? So in our problem up here, we knew the pitching moment at the half chord, and so I'd have to plug in the pitching moment for the half chord there and 1/2 for the x over c value, right? And if I do that, and then the normal force, then I can find the center of pressure. Okay, so there we go. We can add a column on here, up here, where we could find the center of pressure for the airfoil, and we could compute that at every angle of attack. So you've got a different pitching moment and a different normal force at every angle of attack. And so in general, this equation here depends on angle of attack. I'm going to plug in some value for the pitching moment and the normal force based on that angle of attack and get the center of pressure at that angle of attack. Okay. Okay, let's take one more step here and look at the other thing that we are interested in. So this was the center of pressure, and now let's look at the aerodynamic center. Okay, so I can go back to my magical equation here. Remember, this is kind of the guts of moving pitching moments around on an airfoil. And remember, I was able to write this same equation for the location of the center of pressure. Let's see if we can just rewrite that equation for the pitching moment at the aerodynamic center. So CMAC, if I knew what that was, minus CN times XAC over C. Right? And that's got to be equal to all these other things that I've written there. Okay, so now I'd like to solve for XAC over C. That's what I'd like to find. So let's first rearrange this equation. And what I'm going to do is, see, I could set it equal to the information that I know about the center of pressure now, or I could use the information about the pitching moment at the leading edge. But I'm going to keep it in this general form where I just have the pitching moment at some location, and I know that location here. So I'm going to keep it in this form here and just rewrite. I'm just going to simplify here. So we've got CMX minus CN times X over C is equal to CMAC minus CN times XAC over C. Okay, so we see these two terms here. Those can probably be combined. Well, no, we're going to try to solve for XAC over C, right? So actually, maybe first, let's apply our definition. Remember, our constraint over here to solve for the center pressure was that the pitching moment at the center pressure was 0. Well, what do we know about the pitching moment about the aerodynamic center? What's the constraint that we apply for that? Okay, is it that this is also 0? Is the pitching moment at the aerodynamic center equal to 0? That's actually the same constraint that we would have put on center pressure. So that would make those two the same. Okay, Sierra is saying that it's actually the derivative of the pitching moment with respect to what? With respect to angle of attack, Jason says. Right, so we know that the change, our constraint here is that the change in the pitching moment at the aerodynamic center with respect to alpha is equal to 0, okay? So rather than just solving this equation, I've actually got to take the derivative of that equation with respect to angle of attack to solve this. So let's just take the derivative of that. And so we're going to get CMX comma alpha. Now I'm using a comma to denote a derivative. So the derivative of CMX with respect to alpha minus CN comma alpha times X over C is equal to CMAC comma alpha. Oops, that's not a divide, that's a comma. Minus CN alpha times XAC over C. Okay, so I just took the derivative of that equation with respect to alpha for anything that could have been a function of alpha. Now the location of the aerodynamic center we're saying is not a function of alpha, and X is also not a function of alpha, right? So that stayed, and XAC over C stayed, but everything else could in general be a function of alpha. And now I'm going to apply my constraint. CM alpha with respect to alpha has to be 0, okay? So that knocks out that, and now I want to solve for XAC over C. So let's see, if we just divide everything by a minus CN alpha, then what I get is XAC over C is equal to X over C minus CM X comma alpha over CN comma alpha. Okay, so that's the equation that I get there. What we have here from this wind tunnel information is we have the pitching moment at the half chord, and what we need in order to find this is we need the derivative of that with respect to alpha. And remember, we already have X over C is 1/2 because that's the location of where we got our pitching moment information. So we'd plug in a 1/2 there minus, and we'd have to take the derivative of this with respect to alpha divided by the derivative of CN of our normal force with respect to alpha, which we can do that numerically. So we could take the derivative, we could use finite differencing here to get the change in N with respect to alpha, and then the change in M with respect to alpha here, take divide those two numbers, plug it in this equation, and that would give us our aerodynamic center. And we would expect to get something very close to what?
Quarter chord.
The quarter chord, right? So we'd expect, because we're looking at XAC over C, we would expect that that's very close to 1/4, right? And if it's not very close to that, then probably we've done something wrong, right? Okay. So what I intended to cover here was just a review. I think there's been some confusion on what we're doing with forces and moments and how you solve for center pressure, aerodynamic center, and where all that comes from. I just wanted you to see that this just comes from a basic statics problem. What we do is we develop this equation here. This is just a statics problem equation, but then we can plug it in for the center pressure. We can plug it in for the aerodynamic center, and then apply our condition. Of course, the center pressure is equal to 0. The derivative of the moment with respect to alpha is 0 at the aerodynamic center. So those are our conditions, and then we just solve our statics problem with those conditions.